Yeah. Okay, let's go then. Welcome to my presentation. Good to see that people actually showed up for more than just the food. I'm Tim Stokman. I work as a machine learning engineer here at Sytac. I work mostly on computer vision related applications, so not really neural networks. But I actually do build my own models, and I actually, do some more complex stuff. So I'm very glad to be here, and I'm going to focus a little more on the technical details about how machine learning models work and how that actually builds up to LLMs. So, I actually get a lot of questions from people that, when they hear what I actually do for work, they get really curious, and I get a lot of questions about, how do chatbots actually answer these types of questions? How do you build models like that? How can they actually answer questions that complex? How do they actually understand things, right? I mean, I get questions from my interior designer, my little cousin, from the fucker Andres. I mean, you actually inspired like half the presentation. But anyway, how do you actually explain these types of things, right? I mean, fucking cheap little piece. When you start answering that, right? Machine learning models have like a huge history. Was also there are a lot of dead ends, right? A lot of stuff that didn't work, and a lot of engineering itself past these issues. It's innovation, but also a lot of stuff that has been tried out, and sometimes it works. Sometimes it works, but it's hugely fucking complex and takes a lot of compute. And sometimes it's a simple solution to a complex problem. It's, innovation, math, hardware scaling. And it's a little easier if you see these things evolve over the years. So I'm trying to show how these things were built up step by step a little bit. Maybe that's a little easier to grok, maybe not. Ask questions if it's a bit hard to understand. For me, sometimes it's hard to see what is complex for people and what is not complex. So, but yeah, let's take a little bit of walk through history first. So where do these things start? Like in the previous presentation was said, there's history before this, but this is super incomplete and short, but I'm going to try to get the highlights a little bit. So the first idea where people actually try to put, biology, like neurons, the stuff that's in your brain. Don't ask me more because I forgot like 90% of high school biology. But the first idea of artificial neurons was actually from 1943, so very, very old, where they actually started modeling the neurons that are in your brain and try to make a mathematical model of these neurons to try to model human intelligence. So, the idea of artificial people, artificial intelligence was older than this, right? It's a very old idea. Building artificial intelligence, artificial people. But the first real start of it was about 1943. Turing was also a very big part of it. So I'm sure most people know about the Turing test. How do you actually determine if a machine is actually intelligent? Lately, the Turing test has been considered a little incomplete. Most chatbots actually pass it, but we can't really call them actually intelligent, fully intelligent yet, but they can pass that test. So good start, but first, the first checkers API was actually built in 1951. Right now, we don't call this AI anymore, right? A lot of the stuff that they used to call AI is not called AI anymore, right? People solved checkers, chess, etc. Right now, these are search algorithms. You do some clever searching, you judge your positions, and it's not AI, it's just calculation. We know how it works, so now it's not intelligent anymore. That's basically it. It makes some degree of sense. The perceptron, 1957. Do people know what the perceptron is, actually? Show of hands, maybe? I see a few hands. Good, good. So that's a very, basically perceptrons are a very basic, simple concept of the artificial neurons. About at the end of the 70s, there were a lot of reports about, there were a lot, in the 60s and 50s, there were huge money investments into machine AI, machine learning AI, machine translation. Most of that stuff failed with the current techniques that they had, the current hardware. So there were a lot of reports, limitations, theoretical limitations of neural networks. So, and basically there was most of the investment dropped off there. But all the way near the end, they did invent backpropagation, which is still the basics of machine learning today, just before all the investment dropped off. So very interesting. It's kind of a pattern that you see happen more. So same thing happened here. So a lot of the stuff in the 80s was about knowledge-based learning. So what they did is, I'm sure everyone has heard the phrase, it's not an AI, it's just a bunch of if statements, right? I'm seeing a lot of heads nodding. That's basically expert systems. A lot of the 80s, they had like big investments in these systems. They just encoded a lot of knowledge into rule sets, right? And they made huge databases of how knowledge worked. And well, these systems could answer a few questions, could reason through a few things. They did actually pretty impressive stuff, but it was basically a dead end. It didn't get very far. So, but they also did some very interesting work. They invented recurrent networks, more on that later. Some interesting systems that convert text into speech. LLMs can also do that. Some interesting theoretical approaches. They prove that neural networks with more than one layer can actually approximate any function. And that is some of the basics of what later will become deep learning. Q-learning, some of the reinforcement learning stuff, also still used in large LLMs, more on that later. And well, due to, a lot of the investment was in expert systems, and these failed, basically. They didn't do anything actually useful once you put these things in production. Well, they can answer a few basic questions, and they can do some basic reasoning sometimes, right? Based on logic. But yeah, a lot of the real world stuff, it's a little more complex. So if you just use straight up logic, programmed out rules, well, then your system is just a bunch of if statements. It can do some stuff, but it can't get very far. So researchers learned from that, right? So early research focused on logic. They was philosophically driven. People had an idea in their mind how intelligence should work. But is intelligence really that pure? So scientists and a lot of philosophers, they wanted a very pure version of intelligence, pure logic, pure reasoning, no bias, just clear answers. But actual intelligence is a little bit more complex than that. So starting from the 90s and 2000s, you actually get the more modern view of machine learning. And the focus was very early on, do what works. So this is basically called the data-driven revolution, right? It's a focus on benchmarks, public data sets, benchmarks, and build models that actually solve the problem. So one person scores 80% on the benchmark, or the other guy scores 85%. Well, then the other guy must be right. Must have a better technique. You publicize the paper, etc. So very much competition based, and that gave rise to a very rapid evolution of new techniques, new models, new ways of thinking, and the stuff that actually works comes out on top. So you get a steadily rising line of steadily better working models. The road to powerful models contains a lot of very small improvements, engineering, building up, until we get stuff that, can talk back to you. And it's not just a conceptual problem, but it's also, the work of hundreds of thousands of researchers all making small improvements. And some of those rise to the top, and, well, we build on top of that. So, this is if you read a lot of papers, these are the type of papers that you see. So the big ones, of course, are the new innovations. We have a new technique, a new concept. Look how well this does. But a lot of the researchers also, start making observations about it. How do these networks, models work under certain conditions? What happens if you train it like this? You get a lot of interesting stuff from that. You get theory from that. So usually with machine learning, theory is like 10 years behind what happens in practice. You can make a lot of mathematical theorems about things, but usually what comes first is we plug in a lot of models and see nice behavior happening. And 10 years later, we might have some idea about why it is working. But this is important, right? If we know why things work, we can build better stuff and extrapolate from that. And a lot of stuff is, spreading innovation. We'll talk about that later. So Google did a lot of internal research on transformers, and only later did other people apply that to the chatbots. So the people thinking up the new techniques weren't the one that actually made these techniques useful. And also a lot of aggregation papers, all the 20 ways that you can solve this, etc. So that's data-driven research, right? Benchmarks, a lot of researchers working on these types of problems. So I'm gonna just walk through a lot of the components that are contained within a neural network. And we're gonna start with the basics. How many people have actually built their own little toy models themselves, just to try it out, just from scratching code? I see a few hands. How many people remember some stuff from high school math? Okay. Well, I see a few hands. So, what is a machine learning model, right? It starts with this. We have a target value, right? We start with input, and the input can be an image, can be text, it can be a bunch of numbers. We have a model. What is a model? A model is basically just a function. We have input, and it does some calculations on those numbers, and it generates a bunch of output numbers. That's it. Input numbers, output numbers. It makes a prediction, and that prediction might be a little different than the one you expect, right? So, for example, we have a dog-cat predictor. We input a picture, which is just a bunch of numbers. It outputs, hey, this is a cat. No, it's not a cat, it's a dog, you fucking stupid piece of shit. So there's a predicted output and the actual output that the model should output. The difference between those things is called the loss. So we want to make this smaller. We want the model to actually predict the things it should predict. That's the loss function. how do we do that? I already showed that earlier. That's called the backpropagation algorithm. I'm going to show a little later how that actually works. But we're gonna, we want this to be smaller. That's the basic thing. We have a little bit of a function, and we want this magic function to predict the things we want it to predict. Most of these functions are in layers, right? This is a neural network, so this is a model based, that is a little bit modeled based on human intelligence, so human brains. It's biology inspired originally. Right now it doesn't look much like like your biological brains, at least from what I remember from high school biology. It's gone a little weirder. I mean, I don't have a transformer in my head right now, but originally it was inspired by biology. It's also layered. Let's just look at what's actually going on there. So we want to minimize the loss function, right? So what backpropagation does is all these models have parameters, right? I'm assuming people know that. This model has, let's say, 1, 2, 3. This is 8. Okay, there's 11, 12 parameters in this model. We want to tweak all these parameters so that it gives the right answer. That is the basics of machine learning training. How do we do that? We do differentiation. Like I said, high school math. Do we know what function differentiation is? Functieafgeleiders, just for the Dutch people here. Can anyone translate? So what we have is, for example, here is how we optimize a model with one weight parameter. So this is for one parameter, right? So actual models have 100 billion parameters. This is optimization for one parameter. So we have the weight on the x-axis, the loss on the y-axis. The parameter starts at this value, and we want to go all the way here so that the loss is smaller, right? How do we do that? If you just calculate the loss initially, you go here. What we do is function differentiation, and function differentiation calculates the gradient, which means that you get the direction you need to move your weight in to decrease the loss. So if you can calculate this angle, right, this slope, you know which direction you need to move the weight parameter in. So for each weight, we know what direction we need to move in to make the loss smaller. So this is for two parameters. So remember, we don't always know, we only know the direction, so we don't always land in the place where the loss is the smallest. We can always go here, where it's not super small, or we can go here where it's actually minimal, right? So it's a little bit like you're in a dark room. You can only like do this and do. This is for two parameters. Imagine how complex it can get if you have 100 billion parameters or 10 billion parameters. It's a 10 billion dimensional space that you're trying to navigate, right? So this is like this is easy for two, but super complex if you do it with 10 billion. But okay, let's move on a little. So one of the early innovations or early theoretical groundings that machine learning had is that one layer of neural networks can compute almost nothing. can only do very simple computations. If you add layers, it can basically the whole idea is that in order to actually model something actually genuinely complex, you need to add layers. That's the easiest way to add, computational power to your model, right? Each layer can, this is a good example here. So one single layer of neurons, they can only learn a linear function. So this is a very good example. This is one layer, can only learn one linear separation of input data. So only linear functions can be learned with a single layer. If you add one layer, it can do a little bit more complex shapes, right? It can separate, the whole idea is to separate the input data into different types of boxes. With just one layer, you can do a lot more complex stuff. Well, so let's take an actual computer vision model that's a little bit more complex. So you actually also showed the map with maximally activated features, right? So this is a little bit similar. So this is a deep learning model. I think these are feature maps for a Google computer vision model. So the first layer. So this is a fully trained model. How does it actually determine from something super basic, like input pixels? How do we actually determine if something is a dog or a cat, right? Well, people have tried to visualize these neural networks to get them to understand things a little bit more. So this is one of the possible visualizations to see what types of inputs maximally activate each layer. So for the first layer, it's activated by very simple textures and lines. So this is basically edge detection, line detection, right? So it tries to find lines and simple shapes. Next layer, you actually see some more complex textures. It tries to do some sort of texture recognition. Next layer after that, you start to see more complex patterns, right? So, a little bubbly, I don't know what it is, but it's you can see, and remember, each layer can use the information from the previous layers to make more complex decisions and detect more complex patterns, right? Next one actually starts to detect object parts, and so it can detect flowers. I don't know. I don't recognize any of this shit, but it looks a lot more complex. But yeah, it
on the MacBook.
Oh, well. But yeah, it builds on top of each other, right? So if you make a model broader, all the computation has to be in parallel. If you make the model deeper, it has to build on top of each other. Each step can build on the previous step. And hey, this looks a little bit more recognizable if you're on drugs, but it's a dog. Hey, well then, but yeah, it's so this is almost object. It gets activated by more larger objects. So each layer gets built on top of the previous layer, and depth really adds to the computational power of your network. Well, can you actually train these types of deep models very easily? Well, not really. Turns out that deep learning models, if you just, add 1 billion parameters and 20 layers, they're kind of difficult to train. So, first of all, it's very easy to overfit. Does anyone know what overfitting is? So we're trying to learn this function. So x versus y, right? We want this input, we want this output. Well, you don't want, one of the trickiest things is that if you have a 10 billion parameter model, it can learn the training data exactly. So it can, draw a line like this, and it can exactly fit your training data. But when you do something outside of your training data, it's still gonna give the right answer if it's gonna learn this little function here. I don't think so, right? You want your models to generalize. You want your models to make predictions outside of what it has seen before. You don't want it to memorize your training data. And that can be a little tricky. You need to kick your model in the right place to make it behave a little bit. So you don't want it to overfit, you don't want to underfit. You don't want to make a model that's too simple. You also don't want it to exactly fit the training data that you push in. You can get numerical issues very easily, things like exploding gradients, vanishing gradients. If you make your models very deep, we want to calculate the gradients of all your parameters. If your parameter is 20 layers deep, then it gets a little tricky to see what exactly the effect is of your parameter on your loss function. And if you can't calculate that, then you can't really learn the correct parameter. So you also wanted to generalize more beyond your training data. I already said that. Your learning landscape can be very complex. Like we already saw, don't want to go back that much, but we already saw, right, the whole 100 billion parameter space can be very super complex. It can take a long time to train these things. You can have a noisy, bad data set. You can have bad gradients. Hardware is a very big part of it. I can't go too deep into hardware because I'm gonna already go far over time, so I don't want to go too deep into hardware, but that's a whole engineering problem separately, scale towards a 100 gigabyte model, 200 gigabyte models, train that on 16 GPUs, distributed training. You need really good software engineers to make that work. And a few $100 million. You can make it over to my account if you want. I'll get it done. But so one of the solutions that you can start with is called regularization. Which is basically, in general, forcing the model to find regular, normal solutions, right? Solutions that make sense and don't go off the rails. This is actually kind of a hard problem. Some of the earlier solutions were super complex and didn't really work that well, so I'm going to skip those and focus on stuff that actually does work. I'm going to go over these very fast. It might not make sense. So gradients can grow super large or super low. So simple solution, gradient clipping, set a maximum, that works very well. Models go very fast off the rails if you start, depending on the initial weights that you have. So good weight initialization is very important. You can make sure that the model doesn't overfit your training set by stopping earlier. This is a somewhat older solution. I'm not a fan of this because that makes if you have to do early stopping,
You mentioned weight, which developers should kind of set when they do something, but doesn't it make LLM or model, whatever, biased to some preferences?
The initial weights are usually random or from a previous checkpoint. The problem is if you initialize the weights in a non-random way, you can get a lot of numerical issues. So weight initialization is more about cleverly, randomly initializing your initial set of weights to make sure that the trading is numerically stable. And for example, the first time I tried transformers, I didn't get anything done. And with a few small simple tricks like weight initialization, you can actually, get stuff done with a transformer. Just when they first, released transformer software packages, they didn't do any of that shit. So I tried a transformer model and I was like, what is this shit? It doesn't work, useless. But yeah, okay. Sometimes you just need a few minor, seemingly useless tricks to actually get this stuff working. So, like I said, a lot of this stuff is numerical issues. So batch normalization means that at every layer, you normalize your inputs so that they don't go too low or too high. So if you get an output that's in the 100 million range, you normalize it to a range of between 0 and 1. You can use your loss function very creatively to make sure that the model behaves. So you can assign penalties for weird solutions or gradients that go very high or very low, so that you can stop numerical instability in your model. And a lot of these tricks are basically just necessary to get deep models to actually train. One of the nicer tricks that I actually like very much is dropout. And this is a way to force the model to generalize in that you take away parts of the model every time you train. So you make sure that it can't depend on any single feature or any single path to make a decision. So, a dog without an ear is still a dog. So if you take part of the input data away or part of the features, then it still needs to make a good decision. And with dropout, you basically shoot holes in your model each time and force it to adapt. So augmentation is also good. Input data is a cat, just a bunch of pixels. If you turn the cat around, it's still a cat. This is a way to, augment your data and make sure that you have enough data. So the model also learns which types of transformations it shouldn't look at, right? So if the image turns darker or brighter or turns around, doesn't make any difference for the output. Skip layers, so this is still used sometimes. It's also a very elegant solution in my opinion, in the sense that sometimes if you have a super deep network, it forgets information from earlier layers. You just ensure that the information can flow past layers. It can skip layers, and at the very end you can get information from earlier layers without any intermediate transformations, right? Skip layers. Very, very, very elegant solution. It's not used that often anymore, but for some networks, still very relevant stuff. We already talked about how you use gradients to make steps, right? So the basic algorithm is called gradient descent. Just using the direction of each parameter to make steps and to change the parameters in that direction. That can run into very many problems. So you can learn very slowly, just make super tiny steps and take hundreds of epochs until you get a good model. You can learn super quickly, bounce back and forward, and never get to any good model because you make jumps too big. So you want to carefully adjust how big your steps are. Learning rates, schedules. Basically, you start with a high learning rate to make big steps at the start, and then slowly decrease your learning rates to make sure that the model can fine-tune. Adam can do dynamically adjustable learning rates. You can do a learning rate per parameter. Super expensive, but can be effective. So activation functions are also very important. Activation functions are in between each layer. In between each layer, they define a transformation from one layer to another. These things can in a very big way impact the stability of your algorithms and your model. So usually in the past, in the 90s, neural networks had these functions. Can anyone tell me, if you want to do gradient descent, what the problem is with the heaviside activation function? Any takers? What?
Huh? Goes to infinite? It's an infinite step.
Infinite at zero, you mean, or?
Yeah, like
Yeah.
it's just going straight up, the
Yeah.
slope.
Yeah, basically. So, to know in which direction we want to move each step, we need a direction. Here, the direction is zero. Here, it's infinite. Here, it's zero again. I don't know how to actually train the model with this thing, but I can't imagine it went very well. So, the first simple thing you can do is do something like sigmoid, which just smoothens things out, right? This means that you always have an angle to pick. You want a direction to move in with your parameter. So sigmoid means that there's always a slope. It's never infinite. The problem with sigmoid is that if you go very, very low, then it's about zero here. And it's also, if you go that direction, it's also almost zero. It's never completely zero, but it's almost zero. So you have a lot of variations on this stuff, right? I'm not going to go over all of them. I think Swish, Gelu, whatever is very popular in LLMs right now. This one, has more of a direction just about anywhere. But in the end, why is Swish better than Shilu? Now, well, the number goes up faster. A lot of the stuff is just, we don't really know why it works better, but the number goes up, right? Data-driven research. Number goes up faster, so it's better. Well,
That's quite scientific.
yeah, very scientific. Maybe in 10 years we'll understand why the Swish function actually does better than sigmoid, but right now it works. And that's a lot of the LLM stuff, right? It works. So, how do we actually do text? You already mentioned it a little earlier, right? Very early at the start, it's about problem formulation, right? So classic machine learning models are like this. We have an output, and we have the expected output. We have an input. We want to minimize the loss function, right? Well, how do we actually answer questions like this? Well, those are generative models, recurrent models. It's just reformulating the problem statements, right, a little bit. These are still machine learning models. We still have an expected output, but the really clever insight, I think the first guy to do it was in the 90s somewhere, is that we mask our training a little bit. So we cut away one word, and this word is the output that we expect, right? And this is the input, the sentence that was previous there. So we cut away what we do word masking, and we say, okay, this is the input of the model, this is the output of the model, and if it gives a different output, then we want to minimize the loss. We can do the exact same thing, right? We can minimize the loss and walk through that 100 billion parameter space and just see where I need to go. And then, make sure that the model is sufficiently computationally powerful to actually understand the problem. And just like I said, you saw the earlier examples where we visualized each layer. Well, each layer, actually, we'll show that later. If you make the model computationally powerful enough, it can start to model concepts and give good answers to, well, this problem statement. So let's move on a little. So very early in the game, they actually modeled things on human intelligence, or how they thought humans actually worked. I don't think humans have the 10H function in their head, but, well, I might be wrong, I'm not a biologist. But one of the earlier attempts was LSTM. How does LSTM work? They have memory neurons, and they model the sequence one step at a time. So they only look at one character at a time, and they remember the context with their memory neurons. They have a mechanism for forgetting things, they have a mechanism for remembering things, and they have a little bit of state in them. And each step that you take, it only looks at one input, and the rest of the context of your, well, we saw earlier how large context can get, right? 100,000, a million, and they only keep their state in one little tiny memory neuron. I mean, sometimes I forget to close my door behind me, so I'm not sure if you want to model these types of tasks on human intelligence. They thought this was how humans actually work, but yeah, this is very limited. So LSTMs, they are not super efficient. They only look at one thing at a time, and they have a little bit of memory inside of them to remember things. But can that memory actually model the 100,000 words that might have been seen previously? Well, not really. So LSTMs are actually kind of good for short contexts, very short, short text, short videos. I've used the LSTM for video modeling actually. It worked quite well for short clips, but not for longer ones, because it very quickly forgets things. No matter how large you make the memory bits, it starts to forget things. So, what is the solution for that? So, LSTM was actually very popular around up until 2015, 2016-ish, until we got the transformer and the attention mechanism. So this is actually invented by Google, and it basically solves the problem of LSTM in the sense that LSTM only looks at one thing at a time and needs a memory mechanism to keep remembering your context. LSTM looks at the whole input all at once. So it's basically a replacement for LSTM. It looks at the entire sequence at once, and it's a very clever mechanism. So transformers have a query operator, and the query learns to look at where in the context it actually needs to look at. So, for example, you can have a query about, okay, in this sentence, I want a query operator that finds the subjects in the sentence, or all the things related to this or this concept. And the query, after the query is done, you get an operator that actually calculates the result of that query. So it takes the input from the query, it does another calculation on that, and it can match anything with anything. So this is super expensive computation. It's actually quadratic. So if you have a context length of 100,000 words, it takes 100,000 times 100,000 in computation time. So that's why context scaling is so super expensive. It's also multi-head. So you can have multiple operators in parallel, basically. So each transformer is also in parallel per head, and each head has its own query and value calculation. So basically the transformer is also executed in parallel, and you can have 10, 20 different heads all at once in one layer. So one of the answers to how do you make this model more computationally powerful is that instead of making super deep layers, actually make one layer super powerful. And well, that's also turns out to be a very good solution, because a lot of the tricks and numerical instabilities that you have with super deep models also go a little bit away with transformers, because they don't tend to go super deep. You might have 5 layers or 10 layers. Some computer vision models can easily have 120 layers. So you have less deep models, but each layer can do a lot more and can look at the entire sequence at once. And that's the core innovation that the transformer had. And there's always a difference in theory and practice, right? Because Google didn't put this in, well, to good use. They actually followed up with this with the BERT paper. not sure if I'm sure. That's one of the language models based on the transformer. BERT was bidirectional, so it masked one word. It turned out to be a little bit of a dead end. Bidirectional models are still in use, but OpenAI started with, well, people started with the GPT model, and that's one directional. So one directional means that it only looks at the next word. So the winning approach for LLMs was not thought of by Google, but they did invent all the components. Yeah, some other components was already talked a little bit about that. Tokenization is very important. It prevents sequences from becoming too long. Language is also super high dimensional, so you have multiple languages, large dictionaries. If you want to model all these words, you can't really train a model on that if you have 100 million words from different languages that you all mix together in one input. You can't realistically train a model from that, so that's why tokenizers are there, right? It's already talked about that a little bit. Earlier approaches to tokenizers did it per character or for a whole word at once. Both have very big disadvantages. Current best practice tokenizers are tokenized parts of words and well, basically transform these into numbers that the LLM can actually understand. A lot of the limitations of LLMs also come from the tokenizers, so it needs to be chosen, well, in a clever way. But also the reason why it's hard for LLMs to really understand numbers because of tokenization limits. But yeah, I was already treated to this one, so I'm not gonna stop here too long. So yeah, so if you put all these things together, you see a lot of interesting stuff coming up, right? So this is a very early experiment by OpenAI that had some very interesting results. They were actually able to find a sentiment neuron. So does anyone know what sentiment analysis is? Any hands? I see a few. Okay, so what sentiment analysis basically does is it classifies text. It's one of the early natural language processing tasks that we actually want to see if text is positive or negative, if we're cheering for someone or booing them, right? So it's good for analyzing reviews, right? So see if a product review is good or if a social media post is super negative. That is sentiment analysis. Large language models don't have sentiment annotation, so no one is saying, hey, this is a super positive text or a super negative text. But what we do see is that in LLMs, the LLM does model this task, right? So by building super powerful models and by layering them and by training them on huge amounts of data, you see a lot of emergent behavior. This is one of the examples from this, is that they were actually able to find the specific weight and piece of the neural network that understands the sentiment of the text, so that the model doesn't switch from negative to positive in the same sentence, or it can actually, it's part of understanding the text, is also understanding the sentiment. So we're actually able to find the specific neuron that does this, and they can flip it from positive to negative around. So if you want like a super negative chatbot that constantly insults you every time you ask a question, well, then you just flip the sentiment neuron. It's as easy as that. So they've done a lot of experiments, and they can actually show that in all these layers of your super really computationally powerful model, it actually starts to model concepts, right? And well, we don't fully understand large language models, so the theory is 10 years behind the practice. We just plugged together a lot of components and got something powerful, but a lot of people are running experiments, and it can actually see, hey, this is where the model models this is where the model models that. They can tweak a number of parameters and steer the model in certain directions by, making a number negative or positive. Yeah, so this is the end of my presentation. So one last slide about the future. So I'm sure everyone is wondering, are we going to go to true AI? How long is that going to take? Well, I don't know. People were super surprised that language models actually worked, right? They didn't think it would work. And when it worked, it was a surprise for the researchers that it worked so well. Are we done with the exponential growth graph? I don't know. Maybe in 2 years, all programming will be optimized. Maybe not. I think it might take a little longer than that, but feel free to. Reality has a way of surprising you, right? Yeah, it's hard to predict where this is going. Have we reached the limits, or are we going to go to a little bit of a slump before we actually go to actual true intelligence? What is missing? Well, a lot of people are plugging away at the answer, but how long is very hard to predict. People thought that we would have fusion powered power plants right now, right? But 5 years? Maybe 5 years, maybe 40 years. It's sometimes the last part can be super hard. So hard to predict where this is going, but so a lot of recent developments were treated by your presentation, but I'm going to go over them a little quickly. You see agent workflows, chain of thought. Is that the actual solution towards making the models reason, or is it just a computation trick? Well, I think we might see some better tricks in the coming years. Yeah, it's a computation trick, but it's a little bit inspired by how humans think, like short-term thinking, long-term thinking. By spending more tokens, you force the model, to actually make more, reason more. But is it enough? We need to scale up. There are alternatives to transformers that are cheaper, like the Mamba operator, for example. I've run some experiments with that. It's not exponentially complex, but it's n log n, which makes it feasible to have context windows of 100 million, even more. But can it be scaled up to an LLM size? People are still running experiments on that. People are doing reinforcement learning, so actually, making sure that the output of the model, that the model gets feedback on the output. Reinforcement learning is a whole different branch. Can't go too deep into that. But the model doesn't actually get any feedback if it's right or not. Reinforcement learning makes sure that the model is actually trained on tasks that have feedback. So you can feed it a math riddle, and some other part can actually see, hey, is this math problem, is it actually right? And it feeds it back into the model. You can feed it reasoning tasks, and some other component checks if the reasoning is correct. Reinforcement learning will probably be a very big part of making these things smarter. It's not there yet. True intelligence is still far away. How do we get there? Maybe different modalities, maybe, actual robots, putting them in an environment, making them feel, making them learn. I don't know. It's fun to think about, but I probably don't have the answer here. I hope you guys enjoyed my presentation. I hope it didn't go over everyone's head. It's hard for me to gouge into the head. Well, that's good. I hope you didn't hurt yourself too much there.